Okay, yeah, thank you for this kind introduction. And I think you have already read my title or even heard it. So actually, let's dive directly into it. So why is it actually important? You all know in worldwide, there are not a lot of nuclear facilities in operation. So nuclear safety is a very big topic. In these power plants, the piping is usually made of chromium nickel steels, so stainless steels to get rid of corrosion. However, it's an austenitic stainless steel, but at least in Germany, I'm sure for that, the austenitic microstructure is metastable. So metastable means actually the trip effect, so the load-induced phase transformation from austenite, which is FCC, to martensite BCC can happen under cyclic loadings or in loadings in general. So the goal of my PhD and the project is actually to get this phase transformation into CPFEM framework, so crystal plasticity finite element, and at the end, just by numerical simulations predict full Wöhler diagrams. Therefore, there are a lot of different steps I need to do. First of all, we need to create microstructure models, so 3D SRVEs. With Dragon, I come to that in a bit. We need to somehow identify transformation criteria. So in that case, we modify UMAT subroutine for Abacus, calibrate the CP model at the end. And the final goal is, as I said, to get rid of experimental tests, but to depict the Wöhler dynes just by numerical simulations. So if we dive now into the material, which is also in my title, so it's austenitic stainless steel. So the main elements are chromium, nickel, and also a little bit of niobium. So nothing special here. But if we now have a look at the microstructure, which you can see here, we can see mainly austenite. I say mainly because we also have a little bit of martensite in here, these darker gray packets. So it's an austenitic stainless steel, but we still have martensite in there. But if we now electropolish the sample, we get rid of the martensite, which is an indicator that this martensite transforms just because of the mechanical grinding and polishing. So even if you're not familiar with the material, you get a sense of how sensitive this material is to this phase transformation. So for this micromechanical fatigue modeling part, we need two parts, micromechanical modeling and a microstructure model. So for the microstructure model, we go into an EBSD. We make EBSD measurements in SEM. So this is actually the round bar I have, and we cut it appropriately. And here you can see a relatively huge EBSD image and a phase map. And you can see, except some smaller martensite islands, everything is austenitic. It's an electropolished sample. So it's less than 1%, so we ignore it currently, the effect of it. If we have a look at the texture and the pole figures, we can also see that it's quite random. We don't have a sharp texture, so no rolling texture and so on, which is already very good. So we can quite easily build our REs, let's say. And what we also need to do, I hope you can see it. This is a phase map again. So on every austenite grain, we have ellipses fitted on them. So with these, out of these ellipses, we can extract the grain area, the aspect ratio, the slope, and of course the oil angle, so the texture. And all of this data and the interdependencies between all of this data, we're putting into a neural network. In that case, a Wasserstein generative adversarial neural network. And to explain it a little bit easily and non-scientifically at all, we have a generator, a criminal, and a discriminator, which is the policeman. So the criminal creates counterfeit money, so fake money, and gives it to the policeman. The policeman gets this fake money and also the real money, and he can distinguish it at the beginning. Okay, there's fake money and this is real money. However, because the policeman is a little bit shady, let's say, he will give a feedback to the criminal and tell him, okay, this is the reason why I know it's fake money. And out of this feedback, the generator or the criminal learns how to get this data, the synthetic data, in a way that the policeman or the generator cannot discriminate anymore, which is shown here. So these are then the data we get now back to the EBSD measurement. So area, aspect ratio, slope, texture, and so on, and its interdependencies. And as you can see, the blue is fake and orange is real. So the first try, the distributions are not matching, but after a while, quite fast actually, they are the same, so they are matching. So the generator is then able to create actually an infinite number of synthetic data sets which follow the real underlying distributions. And this data set we are feeding our Dragon. So I don't want to go into detail right now. Dragon is an RVE generator that we developed in our lab because we were not happy with the ones that were available, like Nepa or Dream 3D. It's open source. You can try to use it or get in touch with that with us, of course. And actually, Dragon is using the synthetic data sets and creates RVEs, so this representative volume elements or microstructure models. And also, we are able then to create an infinite number of them for some statistical distributions at the end for our values. Okay, so now we have our microstructure model, but we also need a micromechanical FEM model, a crystal plasticity model. Here, to get briefly into some theories, as usually, the deformation gradient is separated into some parts, usually elastic and plastic. But if as here is the phase transformation is very important, we also need some transformation part. We have a phenomenological flow rule, so it's not dislocation based, but just phenomenological. However, it's gradient enhanced, so a non-local model with this super GND concept. I don't want to go into detail here. We have some isotropic hardening, which is incorporated, some kinematic hardening, but the most important part for this thesis or this project is, of course, the Martensitic transformation. So here at the bottom, we have then the respective part. So it's a Martensitic lamellar hardening. And I want to rest it here. I don't want to go into detail. I could go on and on and on and still show you some continuum damage mechanics or crystal plasticity mechanics equations. We don't care about that too much. I want to show you some first results I have. So the fatigue modeling part. In fatigue modeling, there are different parameters, usually some fatigue indicator parameters that are extracted. One of them, or which is often used, is the accumulated plastic slip. And the accumulated plastic slip is nothing else than an indicator for persistent slip bands and hence crack initiation. So here we can see one example of this RVE, which comes out of our Dragon. And if we now have a look at the Martensitic evolution, so this is just a first trial run, actually, with just some parameters out of the literature. We apply some strain controlled amplitude with 0.1 hertz, 0.1% amplitude for 50 cycles. And what we'll see here now in a bit, we can see clearly that the Martensitic, as in literature and experiments, evolves with a number of cycles. And especially this exponential part is also found in literature, which is very nice. So we can see that the model is capable of predicting this slope. If we now have a look at the accumulated plastic slip, it's also increasing. There's also nothing new, actually, when you're familiar with this topic. And what we can see here now is, don't get too nervous right now, this is not the accumulated plastic slip, but this PMPS value, which is actually nothing else than the grain average maximum accumulated plastic slip. So I have performed some one simulation with and without trip, the same model, same parameters, just phase transformation switched on and off. And what we can see here, so first this is the without trip, so it follows a linear line, so which could be extrapolated up to a huge number of cycles. However, with this trip effect, it somehow deviates, and you can clearly correlate this with the exponential increase of the Martensitic volume fraction. this is expected, that it's not fully linear anymore. And what is usually done to get the number of cycles for crack initiation, usually a critical value of this PMPS value needs to be found. If we now just assume that it's around 2, then we can clearly see that the number of cycles with trip and without trip is higher. This is also found in literature because of some transformation-induced crack closure, also on. So these are my results so far. So everything works until now. However, now comes the big research question, how to deal with it. Because usually the accumulated plastic slip is extrapolated until a huge number of cycles, because it's linear. This is not possible right here anymore. So the big and also my open question is how to deal with it at the end. So of course, these are just some preliminary results. There has to be a lot of investigations still. Of course, other RVEs to get a certain statistic, other frequencies, other amplitudes, and so on. Maybe even a higher number of cycles. And how does it look like? So I'm currently happy with that, but also encouraged to find out a little bit more. So that's everything from my side. If you have questions, comments, please go ahead. Otherwise, thank you for your attention.